We're always hearing about how hydrogen is the future of clean energy. I mean, it's the ultimate fuel, right? The only thing it leaves behind is water. So, if it's so great, where is it? Well, today, we're going to look at a really cool technology that might just bring that future right to our doorstep. How? By making pure hydrogen from the fuels we already use every day.
Yeah, it's the big question, isn't it? If hydrogen is this amazing, clean fuel, what's the holdup? Why aren't we all zipping around in hydrogen cars or powering our houses with it? Well, that's exactly the puzzle we're going to unpack in this explainer.
So here's the heart of the problem. It's really a big mismatch. On one side, you've got fuel cells. These are the incredible devices that actually turn hydrogen into electricity. But they are super picky eaters. They demand really, really pure hydrogen. And on the other side, well, there's our entire world, which runs on things like natural gas, propane, and diesel. It's a total disconnect.
And you can't just, swap one for the other. Pure hydrogen is a notoriously difficult little molecule to handle. For starters, it's really tough to store, it's expensive to move around, and we just don't have a planet-wide network of hydrogen pipelines and filling stations ready to go. And here's the real kicker. Most of the hydrogen we make today, it's still made from fossil fuels, just at these huge centralized plants. Kind of defeats the purpose, right?
Okay, but what if we could find a way around all that? I mean, a way to just sidestep the huge storage and transportation headaches completely. What if we could build a kind of bridge using the fuel pipes and tanks we already have to make pure hydrogen exactly when and where we need it? Well, that is the absolutely brilliant promise behind something called fuel processing. All right, let's pull back the curtain and see how this thing actually works. I want you to think of a fuel processor as a mini hydrogen factory in a box. It's this compact system that takes a regular, everyday fuel and just transforms it, step by step, into the super clean hydrogen that a fuel cell needs to do its job. Now, the official term for this is fuel processing. All it really means is taking a commercially available fuel, like natural gas from the pipe in your street or diesel, and converting it into something called a hydrogen-rich gas reformate. It sounds complicated, but really, that's just a fancy way of saying a gas mix that's packed with hydrogen and ready for a fuel cell to eat. So how does this little factory work its magic? Well, you can think of it as a three-step journey for a single fuel molecule. First up is fuel cleaning. We've got to scrub out all the nasty stuff that could cause problems. Next is fuel conversion. This is where we crack that molecule open to get the hydrogen out. And finally, there's gas cleanup. This is like the final polishing stage, making sure the gas is absolutely perfect for the fuel cell.
Okay, let's get into the nitty-gritty. We're going to dive into how we actually forge this fuel, how we take a complex hydrocarbon and turn it into simple, pure hydrogen.
So, step 1, cleaning. Before we can do anything else, we have to deal with the number one bad guy in this whole process. The first villain we have to defeat is sulfur. You find it in pretty much all commercial fuels. In fact, they even add it to natural gas to give it that rotten egg smell so you can detect a leak. But for our little hydrogen factory, it is absolutely devastating. And when we say poisoning, we're not being dramatic. It's a real thing. See, the system relies on these things called catalysts. They're kind of the secret sauce that makes all the chemistry happen fast and efficiently. Sulfur atoms literally stick to the surface of these catalysts and just clog them up. It's like putting gum in a lock. It permanently breaks them. So getting rid of every last bit of sulfur right at the start, it's completely non-negotiable. Okay, with the fuel all cleaned up, we get to the main event, breaking it down to get the hydrogen. And there are basically two ways to do this. First, you've got the classic method, steam reforming. You just add steam and a lot of heat, and it slowly coaxes the hydrogen out. It's an endothermic process, which means it needs constant heat, kind of like baking a cake. On the other hand, you have partial oxidation, or PROX. This is way faster. You add just a little bit of air, and it basically creates its own heat. It's exothermic. Think of a self-heating meal pack. The upside is it's great for a quick start, but the downside is you don't get as much hydrogen out of it.
So you've got this choice, right? Slow and steady with a high payoff, or fast and furious but less efficient. But what if you could have the best of both worlds? Well, that's exactly what a third method does. It's called Autothermal Reforming, or ATR, and it's basically a hybrid. It cleverly uses a little bit of that fast heat-producing POX reaction to power the slower, high-yield steam reforming reaction, all in the same box. It's a really balanced approach, way faster than just steam reforming, but with a much better hydrogen yield than just partial oxidation.
All right, so we've cleaned our fuel, we've cracked it open, and we've got a gas that's full of hydrogen.
We're almost there, but we're not quite done. For a lot of fuel cells, especially the ones you'd find in a car, this gas is still too dirty. It's time for the final polishing stage.
So just when we thought we were safe, a new villain shows up, and this one was actually created during the last step. It's carbon monoxide, or CO. Now what's interesting is that for some high-temperature fuel cells, CO is actually fuel, but for the more common, low-temperature ones, it's a poison, just as bad as sulfur was for our catalysts.
So how do we get rid of this stuff? Well, the first line of defense is a pretty clever chemical trick called the water-gas shift reaction. Basically, you add more steam, and over another catalyst, you convert that harmful CO into harmless carbon dioxide. But here's the really cool part. This reaction also creates even more hydrogen in the process. I mean, you get rid of a poison and you make more fuel. That's a total win-win. Now, that water-gas shift gets rid of most of the CO. But for the really sensitive fuel cells, we need to get that concentration down to just a few parts per million. And to give you some perspective, that's like trying to find just 1 or 2 bad apples in a pile of a million good ones. It's incredibly precise. And that's where the final step, preferential oxidation, or PROX, comes in. Here, you inject a tiny, carefully measured amount of air to selectively burn off those last few stubborn CO molecules. What's left is an incredibly pure stream of hydrogen ready to go.
Okay, so we've followed the whole journey. Clean, convert, and polish. You can see it's a pretty involved process. So you might be asking, why on earth go through all this trouble? Why does any of this matter when we think about the future of energy?
Well, here's the crucial thing to understand. Not all fuel cells are created equal. The amount of processing you have to do depends entirely on which type of fuel cell you're feeding. Take a low-temperature fuel cell, a PEFC, the kind you might put in a car. It's super sensitive. To it, both CO and sulfur are total poison. But then you have a high-temperature fuel cell, an SOFC, something you'd use for generating power for a building. It's way tougher. In fact, it can actually use the CO as fuel. And the implication there is massive. It means if you're powering an SOFC, your fuel processor can be way simpler and cheaper. But for that car engine, you need the whole shebang, the full, complex, and more expensive cleanup process.
So let's wrap this all up. What are the big takeaways here? First, fuel processors are basically mini, on-demand hydrogen factories. Second, they're so important because they let us use the fuel infrastructure we already have, like our natural gas network. Third, the process is always a journey. You clean, you convert, and you polish. And finally, and maybe most importantly, just how much polishing you need to do depends entirely on how picky your fuel cell is.
And all this leaves us with a really big question to think about. By letting us use our existing fossil fuel networks to power clean fuel cells, is this technology a brilliant, necessary bridge to get us to a real hydrogen economy? Or is it just a convenient detour, something that actually keeps us hooked on the very fuels we're trying to leave behind? There's no easy answer here, but how we solve that puzzle is going to define our energy future for a long, long time.